In the last video, that was video number 321, we provided an overview of the key reaction that alkenes undergo, that is the so-called addition reaction, where we start off with a carbon-carbon double bond, we bring in some reagent like HCl, and of that reagent, one of the groups adds across one of the two carbons of the carbon-carbon double bond, like we bring in a hydrogen here where I'm highlighting with my laser pointer, and the other carbon of the double bond picks up the other group or the other atom, that's a chlorine in this case, to result in a product where we have added that group into the molecule, and as a result, the pi bond is no longer here to avoid the carbon going over the octet rule. In that last video, we learned how to predict the product of these reactions for some simple symmetrical alkene molecules. Now what we're going to do is look a bit deeper by exploring how the reaction occurs, with our example focusing on the reaction called hydrohalogenation, where we're adding a hydrogen, hence hydro, and a halogen across the carbon-carbon double bond. So we're adding HX haloacids to our alkene molecules here in this case. We use the term reaction mechanism to describe the steps required for a reaction to take place. When we think about reactions, the way that reactions occur is through the transfer of electrons. And so the reaction mechanism shows in a step-by-step fashion each electron transfer that occurs to convert a reactant, such as the alkene, into the product, such as the haloalkane, that we observe as the final product of the reaction. So it's showing here, by step, each electron transfer, all of the reactants, all of the products, and also the intermediates along the way that it takes to get to that final product. So what the reaction mechanism shows us is the logic of how a reaction takes place, to illustrate to us that the reactions aren't simply magic. Instead, we can rationalize how they occur in a step-by-step systematic fashion that follows logic. So what we're going to do in this video is introduce that logic with regard to our hydrohalogenation reactions by looking at the hydrohalogenation mechanism, the series of each electron transfer that takes place to go from reactant to product. We'll do this for our example starting structure of 2-butene. Specifically, I'll use cis-2-butene. I could have used trans-2-butene as well. I'm doing the condensed structural formula here for this. And we're going to react with HCl, which I could write out as plus HCl like so, or I could have written it over the arrow as well. It's equivalent one way or the other. I'm going to show all of my lone pair electrons in these structures to fill the complete octet of all of them. In the case of reaction mechanisms, it's useful to show all those electrons because it's the electrons that are doing the work within the reaction mechanism. The atoms are just following along for the ride. What happens in the hydrohalogenation mechanism, if we want to describe it in words, is that the pi bond is mobile and pi bonds react with acids. And so what happens is that the pi electrons do what we call attack the proton from HCl, the acid. Acids are highly reactive. That is why they have so many impacts. And what happens here in this case is that the pi electrons, that would be the electrons from the second bond right here, are going to come over and they form a bond to the hydrogen atom there. And we're illustrating this with our so-called electron pushing arrow. The electron pushing arrow, as I will call it, is what illustrates the flow of electrons, where the beginning of the arrow right here indicates the starting point of the electrons. In other words, that has to start on either a pi bond or a lone pair, because that's where the electrons reside. And then the finishing point, the arrow head, located right here indicates the destination of those electrons. And the destination of those electrons will indicate where a bond is being formed. So the arrowhead indicates, in this case, where is the covalent bond being formed. So in other words, to illustrate that here, the pi bond is coming over and allowing a bond to form between one of these two carbon atoms, because the pi bond is going to remain tethered to one of those two carbons, we could think of it as, and one of those two carbons is going to become bonded to this hydrogen atom right here. So that is what we'll show in the product of this reaction mechanism, is that we have the same carbons and hydrogens bonded that we always did. I'll show those in orange. And then that pi bond has come over and grabbed a hydrogen. And I'm going to highlight that hydrogen in green here. And we'll show the new bond to that hydrogen in green as well. So in other words, one of the two carbon atoms of the alkene, this carbon or this carbon in blue, corresponding to blue over here, is going to pick up a hydrogen atom right here. And that's going to result in a positive formal charge appearing on the other carbon atom. The reason why that's a positive formal charge there is if we calculate formal charge is equal to the column of the periodic table that carbon is in. If you look at your periodic table, that's column number 4, minus the number of covalent bonds. There's 3 covalent bonds to that carbon rather than the desired 4, and there's no lone pair electrons, and so it'd be 4 minus 3 equals plus 1. So that gives a positive formal charge on that carbon. That carbon is inherently very unstable, and hence highly reactive because it would like to return to a stable state. And the beauty of this reaction is that in addition to generating that carbocation, a positively charged carbon, what also happens here is that additionally the reaction generates a chloride anion. The reason why it generates a chloride anion is because this bond between hydrogen and chlorine has to break, because hydrogen can never have more than one covalent bond at a time. So if we're forming a bond between carbon and hydrogen, something's got to give. Because if this hydrogen atom is forming a bond to carbon, it can't also be bonded to chlorine, so that chlorine breaks away. So we show the arrow there starting at the electrons, as we always do, ending on the chlorine, indicating that bond has broken and the electrons from it have gone on to the chlorine atom. So let's show that. Chlorine then has originally 3 sets of lone pair electrons. It picks up a 4th set donated from that covalent bond breaking. See, the electrons from that covalent bond going over onto the chlorine. The arrowhead indicates the destination of those electrons. That gives us this chlorine that has 8 electrons in total. If we do our formal charge calculation there, we're going to find that results in a chlorine that has a negative formal charge. Now, in the world, opposites attract. That has been said time and time again, and probably has some bearing of truth to it. And so what happens here is that as this mechanism continues, the negatively charged chloride is attracted to the positively charged carbon. And so what goes on next in this reaction mechanism is that the anion, that is our Cl-, uses its lone pair of electrons to attack the carbocation, cation meaning a positively charged carbon. The process is going to occur with our electron pushing arrow showing that the lone pairs from the chlorine come in and they land on that carbon, because our arrow always begins at the electrons right here and ends on the atom. So that's how we know what direction the arrow is going. It starts at the electron source and ends where those electrons are going to land to form that new covalent bond. And this will lead us to our final product of this reaction, where we have our skeleton drawn in. And then I'll sketch out the groups bonded here, our hydrogen and our chlorine atom, like so, giving us our final so-called addition product. And due to the symmetry in this molecule, I could have also approached this problem from the opposite vantage point, meaning that at this first step of the mechanism here, I could have taken that pi bond and had this hydrogen become attached to the carbon on the left or the carbon on the right. In this product, I chose to attach the carbon to the carbon on the right, but I could have equally done it on the left due to the symmetry in the molecule. Doesn't matter which one I chose. Then the next step is always going to be the chloride comes in and attacks the carbon atom here, giving rise to our final product here.